Hey gang, welcome back for another video here on Ochem. Alright gang, so luckily this is another one of those videos where I'm not going to, cover anything new. Everything I'm going to talk about in this video, you already know. The annoying part is that it's, stringing some things together and it's kind of tedious. It's kind of long. This is a video on the Malonic Ester Synthesis. Honestly, a cool reaction. Unfortunately, it's a bit nitpicky in that there's a lot of steps. If you're gonna draw the mechanism, it's a hand marathon. Don't cramp up, pace yourself, and it's really easy to, lose some protons along the way just because it's many steps. But, like I said, if you've been putting in the time, when you run into the Malonic Ester Synthesis, it's nothing new. It's just a combination of a few things you've already put the hard work in to learn. Okay? So, I want to walk through an example a little bit more slowly, then I want to do a second example a little bit more quickly, but this is certainly one of those things where you just got to do a few of them, or a bunch of them, or a lot of them, and you'll be, set. You won't miss it on your test, you'll get all the points, but it truly is, especially if you have to produce the mechanism, something you don't want to waste time on, you just want to have it in your back pocket, like clockwork, as familiar as this sucker right here, the back of the hand. Okay, so the Malonic Ester Synthesis. If I want to write this in words, here's basically what you're going to do. The Malonic Ester Synthesis is, I'm going to number the steps. 1 or 2 alkylations, SN2, we've done that. So basically you're going to have a diester. You will start with one. The diester can vary. Doesn't matter what the ester is composed of. But you're going to start with a diester and you're going to do 1 or 2 alkylations. 1 or 2 depending on how many protons you have available here. If in this case, the first example we're going to do, we have 1 proton, so we're going to do 1 alkylation here. Then your second step, so that kind of covers 1 and 2, right? We're going to deprotonate, we're going to alkylate. So, like, this is, how about this? I'll summarize the steps right here, 1, 2. In step 3, we're going to do two ester hydrolyses. Right, so basically these 2 esters are going to convert into carboxylic acids. And if I'm going to be absolutely correct, since we're doing it in base, they're going to be carboxylates, right? Or, see, this is where the annoying part is. It's a lot of proton transfers, and sometimes people do it differently. You'll see what I mean. So 2 ester hydrolyses, and then hopefully 4 looks very familiar. We're just going to top it off with a decarboxylation. Okay? So, at Malonic Ester Syntheses, if we're going to do this and complete the reaction question, you basically keep one of your esters, but it turns into a carboxylic acid, and you either keep the 1 R group you had to start off with and whatever you alkylated with, or at this position, you have 2 of the groups you alkylated with. So we'll step through an example. This is going to be an example where we do 1 alkylation, then we'll do a second example where we do 2 alkylations. You'll see what I mean. Like I said, you just got to rep a few of them to get, very, very quick at them. Okay, so like I said, don't take what I'm doing here to be gospel as far as, obviously I'm going to do it correctly, but what I'm saying is, if your teacher or if your professor kind of does the proton transfers differently, please do it his or her way. Don't take mine to be the almighty truth, okay? All right, so starting off, I'm going to go ahead and draw a little line because I'm going to need as much space as I can use. So in the first step, right, we see that we have basic conditions, but not just basic conditions that mimic the 1 part of our ester, the ether part of our ester. So we're just going to deprotonate at the alpha position to our 2 carbonyls. So I'm going to take the liberty of just, this is a plus, minus. I'm going to use as much space as I can, so I don't think it's too complicated for you all to start, follow me with if I just go ahead I'm gonna make some space. Sorry, this is getting not enough to the smoothest of starts in this video. Right, we're gonna deprotonate and dump the electrons at that position right there. Nothing new, nothing groundbreaking. Okay. Oh, still have the methyl group. So now we just have a carbanion, right? We've deprotonated, we have a good nucleophile now. So what we can do is enter in our propyl bromide. So, right, this is steps 1 and 2. We're just gonna deprotonate and we're gonna alkylate. We're just doing some SN2. Okay, so at this point, right, at this point in your Malonic Ester Synthesis, just pause and say, can I deprotonate my diester again and do another alkylation? The answer here is no, because we have no more protons to deprotonate. So we're done with steps 1 and 2. So now we need to get on to the annoying hydrolyses, 2 of them to be exact. We need to convert both of these into carboxylic acids, carboxylates, whatever. So this is the part where we enter in hydroxide. Hydroxide attacks one of our carbonyls. Electrons kick up. We form a tetrahedral intermediate. So hopefully you all are starting to see why this is so annoying. It's because you have to redraw a spaghetti monster structure over and over and over again. O-methyl. Remember, the tetrahedral intermediate collapses. We kick off what's not a spectacular leaving group in methoxide. And forgive me, I know I'm not doing like my equilibrium arrows properly. Just focus on the mechanism here. And remember, the methoxide's gonna come back. It's gonna want something. That something is just to be protonated, and it's gonna do that. That's where we get that carboxylate from. And what I've most commonly seen at this point, what I'm gonna do is I'm just gonna keep that charge around. Or you can protonate at the step, you can grab it from water, doesn't matter. So at this point, hydroxide is gonna come in again. We're on another one, that's right, another one. And we do the same thing again. We attack, electrons kick up. We form yet another tetrahedral intermediate. Right? It collapses. We kick off methoxide. Methoxide is pissed, right? Wasn't totally looking to leave, was methoxide. So obviously methoxide comes back with a score to settle, but that score will be settled. Oh, not yet. Sorry, I got carried away. The score is settled by methoxide just grabbing a proton and leaving, and that is how, ladies and germs, we get the 2 carboxylates. So, I know I'm kind of flying through this, but you've all seen these steps already. Right? There we go. So, it's at this point that we move on to step number 4. So, I'm going to, in one step, just show the protonation of this, as well as just, we're going to have a ton of sulfuric acid. We're not going to be short in that department. Okay? So, now we have a diacid, and you can see we have water heat, right? What I'm going to do is I'm going to draw my rearrangement. Also, I'm sorry, gang, my mouth is very dry. Okay, so I'm leaving. What I'm going to do is I'm going to leave this section as it was. I'm going to draw this kind of adhering to that 6-membered-ish ring. So remember, don't ever lose the 1, 2, 3 dicarbonyl. 1, 2, 3, 4, 5, and 6, right? We see these coordinating, right? That's what's kind of the stabilizing force to set up, to make sure we're in position for the decarboxylation. And remember, it is the oxygen taking 2 electrons from the double bond, grabbing the proton. These electrons swing down to form the oxygen-carbon double bond, setting up for carbon dioxide to form. And then these electrons coming over here to form our enol. So I'm going to kind of draw this down here because I'm running out of space. But CO2 gas is leaving, it's peacing out into the air, out of sight, out of mind. And we're left with something that looks very similar to what we have up top. I have my carbon here, my methyl group. I have my propyl group. Oh, I'm going to draw this a little higher. I have a double bond. And what's even stranger is I kind of have almost a double enol. I'm going to draw a line right here to kind of section that off. I have a double enol. And it doesn't matter which one you choose to work with, we're symmetrical, but one of these alcohols in the enol, the enol will flip back to a carbonyl. And that's why we get, I can even draw this a little bit differently up here. Bam, bam, bam. And if you're curious as to how this happens right here, I'm going to go ahead and make some space down here to show that. It's nothing too terrible, it's nothing, too mind-bending. Don't get confused, it's something you've done before. But what would basically happen is, you can draw this also a few ways, but I think the easiest is water comes off, picks this off, these electrons swing down, and then these electrons in the bond, they find a home to be protonated by somebody. That somebody's going to be sulfuric acid. So you can do this in one step. You can do it in not one step. Like I said, the most annoying part of the Malonic ester synthesis is the amount of arrows you have to draw, the amount of protons exchanged, all that stuff. So let me go through this one more time. So remember, for the first 1 and 2 steps, you're going to do 1 or 2 alkylations, right? We're going to deprotonate the carbon that's alpha to 2 carbonyls in our diester, right? We'll start with a diester in the Malonic ester synthesis. So we had 1 proton available, so we knew we were going to deprotonate once and alkylate once, right? The deprotonation, the SN2 attack, did the alkylation with this 3 carbon group. Then we annoyingly had to do 2 ester hydrolyses in base, right? We had hydroxide attack. We formed a tetrahedral intermediate. It collapsed. We brought the alkoxide we made back to be protonated to seal the deal. Then we did it again, right? Hydroxide attack, the other ester. Tetrahedral intermediate on the other ester. It collapsed. We kicked off the alkoxide, which was methoxide, again. It came back. It was protonated. We formed another carboxylate. Then we protonated both. We had 2 carboxylic acids. We didn't have to do it, but we redrew the conformation to set up for the decarboxylation. We drew it. We knew that formed an enol. We showed the enol tautorizing to the ketone form, giving us our wonderful product. Whew. I know it's a mouthful, gang, but let's do one more example and we'll call it a video. Gang, one more Malonic ester synthesis and then let's forget about it for a while. Okay, so here's a new problem. And remember, with a Malonic ester synthesis, you're going to start off with, that's right, a diester. And you can see we have one here. Remember, it doesn't matter what the ester is. You just need a diester. Okay, so remember, the steps for the Malonic ester synthesis is, I'm going to call them kind of 1 and 2. Don't take these numberings as, the truth. I just think it makes sense in my own brain to kind of number them like this. So remember, 1 and 2, and I'm going to say, or more. Remember, you're going to kind of do, you will deprotonate and alkylate. And you'll do that 1 or 2 times. Depends on how many protons you have available on the carbon in between your carbonyls. And looky, it seems like we have 2. So in our first example, we only had 1. Now we get to have twice as much fun. We'll see. So let's just, and then, then we do our ester hydrolyses. 2 of them, right? Always 2 of them. And they're not that fun, so there's a frowny face. And then, last but not least, we end it off in a great ball of fire by doing a decarboxylation. Okay, cool. So, let's just chip away. So in our first step, I'm going to be a little bit better about my space because I ran out of space on that last one. So I'm going to make a little box right here. Okay. So we see we have base. It matches what's in our structure. Clearly, we're just going to deprotonate that position right there. So I think you are all comfortable with the fact if I can just go ahead and draw this. Then we bring in this structure that has 2 good leaving groups. And it's symmetrical. And I lost a carbon. 1, 2, 3. I want to have this to be 4. I'm sorry, gang. 1, 2, 3, 4 carbons. Cool. So let me... Excellent. Okay, cool. So it doesn't matter where we attack because it's symmetrical. But go ahead and attack and kick off one of the good leaving groups. So ETO. So all we've done so far is deprotonate and then alkylate this position right here. 1, 2, 3, 4. So 1, 2, 3, 4. And then a bromine. Okay? Cool. So, wouldn't you know it? Let's go again. We see, and I don't know, like I said, if your teacher, professor writes this differently, some people might only just show these 2 steps, but I'm showing an explicit extra basic step. So at this point, right, we would see OET come back and deprotonate here, dump electrons here. But if that wasn't listed, just know it would happen. It all depends on how many protons you have here. That will dictate how many times you alkylate. I'm going to steal some space up top. Okay, so 1, 2, 3, 4, and a lone pair. Okay, so this problem is a little bit more unique than just a typical kind of double alkylation malonic ester synthesis. I don't need to grab another substrate to attack. I had one substrate with 2 good leaving groups on it, right? And we've seen this thing before in organic chemistry, right? I can just do an intramolecular attack. Right? And then electrons kick off. So we know we're going to form a 1, 2, 3, 4, 5-membered ring. We're always cool to form 5-membered rings or 6-membered rings, especially 6. But 5 works too. So all the way over here, ETO, OET, and then I'm just going to have a nice little pentagon. 1, 2, 3, 4, 5. Bam. Okay, so this part is done. Put a big old X. So we need to do the really unfortunate part and do our ester hydrolyses. So it's tetrahedral intermediate time. So remember, bring in your OH and attack a carbonyl on the ester, kick the electrons up. Sorry, I know I'm drawing things small. OET, redraw the ring. Remember the tetrahedral intermediate will collapse. We kick off the alkoxide piece, and that is not great. But remember, the alkoxide piece will come back with a vengeance, but not too large of a vengeance. We know it's going to play nice and settle for a proton. And that proton will come from the H in what was briefly a carboxylic acid. So we form a carboxylate. Okay. O minus. Cut the ring. Then we just do it all again. Remember, another hydroxide comes. Another. And it's going to attack the other ester. O minus, OH, OET. Oh, whoops, just kidding. O minus, that's a carboxylate. And we got a ring. And if you're wondering at all, you know, could I be drawing a sodium here to balance this out? The answer is yes, but I'm lazy. Remember, tetrahedral intermediate collapses. Oh, and I forgot this. That was not just an ET, that was an OET. Because we're going to kick it off now. And we have played this game before. We have briefly a carboxylic acid. Didn't touch this piece over here in the structure. Didn't touch the beautiful little pentagon right there. So remember, the alkoxide we just kicked off, comes back. It's just begging to be quenched, and it will just do absolutely just that. And that helps us form the second carboxylate. Okay, cool. So remember, I'm just going to cheat and do 2 protonations in one step. Maybe your teacher's cool with that, just to save my sanity. OSO3H. Just going to protonate. And same deal over here. HOSO3H. Okay, cool. Just the protonation step. So now we have exactly what we need. Okay, losing my mind a little bit. Okay, so we've done the ester hydrolyses. Oof. And we cheated a little bit into the decarboxylation. So remember, I'm not going to do anything different in this step. Nothing chemically happens here. Just a structural rearrangement. So there's my... So I'm going to remember, there is this 1, 2, 3, 4, 5, 6 conformation that's so stable for the 6-membered ring reasons and the slight aromaticity reasons. That is when this oxygen grabs the H, the proton. These electrons swing down to help the formation of CO2, and then this bond breaks, allowing CO2 to form and also forming an enol on this side. So over here is where we have CO2 leave, and what we also produce is kind of that double enol action, right? Okay? So it's at this point that this will tautomer back to the ketone. I will do a better job of illustrating this right now. So the way I like to kind of show it is these electrons swing down, reform the carbonyl carbon. That bond has to go somewhere or else it will break the octet rule. Enter in sulfuric acid to help us out. So we reform the carbonyl. We still have this H, right? So we have a positive charge right there. But bring in the conjugate base. Doesn't matter if you use water and hydronium for this. Just choosing to use sulfuric acid. So, woof. This is our final answer. And if you're wondering how you just skip all this for a complete reaction question, the answer is, remember, you always, one of the esters, if you want to draw your product, just have one kind of as a carboxylic acid. You know one of them will leave as CO2. And you know this carbon right here never leaves. And this carbon kind of gets an R group and an R group, right? In this case, right, we knew the point of attachment was here and here. So 1, 2, 3, 4. 1, 2, 3, 4. Bingo. Okay, gang. Like I said, this is one of those things you gotta just sit down and wrangle with for yourself, but it becomes like clockwork once you just get it. Whew. So thanks for tuning in. Don't look at Ochem for a minute, and I'll see you in the next video.